The second half of Chapter 8 is on permutation tests. So permutation tests are the non-P version of tests from Chapter 5. So it's a test for two samples. Just like the two-sample t-test or the two-sample binomial test, but non-parametric. So we're going to have two samples that I'm going to represent kind of generically as coming from distributions fy and fx. So look, I am writing a distribution down, but I'm doing it just in notation. I'm not specifying a particular family with particular parameters. I'm just writing them down as some distribution for y and some distribution for x, because what I really want to know is a relative comparison. Is it the case that the two distributions are the same or different? So I don't want to know any particular aspect of that distribution. I just want to know if they're the same as one another. And even that's kind of overly generic, because a permutation test targets a particular aspect of those distributions via a choice of statistic, which is always true about hypothesis tests, but the particular thing about permutation tests is that statistic is on the combined sample. Okay, so what's the combined sample? I'll just generically notate that as SYX, but what I mean is some statistic that's calculated on the vector of values that you get when you put the x's and y's next to one another in the same vector. So, for example, one such statistic might be the difference in the averages of the two samples, which I would get by forming y bars from the first ny value and x bars from the second nx value. And you might wonder why we've created all this combined vector notation for that, but it will become more apparent when we look at how permutation is involved. Another such statistic might be the ratio of standard deviations. Again, we would calculate the standard deviation on the first ny values in the combined vector, and then the second nx values, and then take their ratio. And the reason we have this combined sample notation is because what I'm going to tell you next. So the idea of a permutation test is, if the null hypothesis is true, that is, if the two samples came from the same distribution, the value of, let's write that better, of the statistic on the combined population, combined sample, I should say, won't change much if you permute the combined sample. That is, if you change the position of the y's and the x's in that vector. Okay. if ny plus nx is small, you can exhaustively enumerate all permutations. A permutation is like a shuffling, right? You can permute a deck of 52 cards randomly by shuffling them. But it's difficult to explore all possible permutations of a deck of cards because there are 52 cards in a deck and 52 factorial permutations, which is a really big number. So if you can't exhaustively enumerate all 52 factorial, or maybe even bigger than that, if ny plus nx is big, in practice, you actually do shuffle. You explore the permutations randomly. So one randomizes. Okay, so I'm going to show you that because that's really what most people do in practice. Okay, we're going to exclusively be in R from here on out, so I'm going to switch off of the notes to make sure I don't mess this up and forget to show you some plot. We're going to carry on from the bootstrap example where we looked at data on fish length. So that was in the vector y, and here in the vector x is more fish lengths for fish caught on another day of fishing. And what we want to know is, do they come from the same distribution? Okay, so I'm going to extract these dimensions. We had length of y as n before, but I want to call it ny now so I can have it kind of match symbolically with nx. Okay, so those are the lengths. Let's form the combined sample. I like to call that yx because we're putting y right next to x. And it should have ny plus nx observations, which I'm now going to call n. And then my statistic, first I'm going to do based on y bar minus x bar. So my statistic on the combined sample. I like to call this b diff for bar difference, the difference between y bar and x bar. So mean, I'm going to take the yx combined sample and take the first ny of them in my y bar, and then mean of the next ny plus 1 up to n of them for the x part of the sample. Now you might be saying, why did he bother with all this yx combined sample stuff? Because I could have done mean y minus mean of x, right? And that's the same, as long as I didn't make a mistake, that's the same as what I calculated using the combined sample. The reason for making the combined sample has to do with the shuffling, or what you might call random permutation. So if I do a random permutation, I'll call that capital YXS, sample YX n. Notice how this is very similar to the bootstrap, but I'm not putting replace equals true. I have implicitly got replace equals false because that's the default argument. So I will not be replacing, so when I sample n from n things, I'm going to get a random permutation. And when I calculate the statistic on that, instead, I will get a different value because some of the original y's have been moved into an x position in the combined sample, and some of the x's have moved into a y position. So when I calculate these statistics, I'll get a different number. Now with the idea being that if I permute them, I should get about the same number. It should be about the same number statistically speaking. So I have to do this a lot of times. I have to save this in some vector, BDS. I'm just going to call it P because I'm going to do 4P in 1 to capital P for the number of permutations. So I'm going to do 10,000 random permutations. Got the random permutation. I'm saving it. I better make some space. Okay, so I think that'll do it. Now I've got a big simulation of all the permutation, of all the permuted differences in X bar and Y bar, and I can visualize them in the usual way. I always like the histogram. Okay, so those are what I get, and then I can put on what I calculated from the data. And I think I'm probably not going to reject the null hypothesis because although that's sort of in the tail, to me it looks like it's more than 2.5%. So when I multiply it by 2, I'm going to get a number bigger than 5%. But I can go through the motions of that. 2 times mean BDS less than or equal to BDiff. 8%. So fail to reject the null hypothesis that Fy is equal to Fx. All we've really determined is that they don't have, that they might have the same mean, and that's only one aspect of a distribution. So we can check another aspect if we want to. How about ratios of standard deviations? What I mean is a standard deviation ratio, or SRAT. So this could be SD of yx 1 to ny divided by SD of yx ny plus 1 to n. By the way, you could look at a difference in standard deviations if you wanted to. It's totally up to you. I've decided to look at a ratio, and if I got a ratio of 1, then they would have the same standard deviation, but it doesn't. It has one close to 1. But that number isn't meaningful in a vacuum. It's only meaningful relative to the distribution of this statistic that we get under the random permutations. So let's go sample from that distribution. Okay, I'll call this I'll call this SR for SD ratio. That stays the same. SR. I need to do SD divide SD. I think that's probably it. Then we'll visualize. Okay, and then we'll put our estimated value on there. Also a close call, but to me this looks like it might be far enough into the tail. So let's do p-value calculation. 2 times mean of SRS greater than or equal to, because we're in the right tail, SRAT. Less than 5%. So reject the null hypothesis and determine Of course, you can check as many aspects as you want, and the multiple testing hazard tells us that we run into a type 1 error problem if we keep testing, because eventually we'll find something that rejects the null hypothesis. We talked about that in chapter 6 with ANOVA, and it'll come up a couple more times again in later chapters. But that's it for now. That's the permutation test.